All right, welcome to the deep dive. Today, we're diving into a realm that I think will deeply resonate with you, given your philosophical background and your inclination towards those big fundamental questions about reality and knowledge. We're going to explore the philosophy of mathematics.
Yeah, it's kind of a unique area, wouldn't you say? I mean, as our main source here points out, the Stanford Encyclopedia of Philosophy entry, it really sits at the crossroads of several major branches of philosophy. You've got philosophy of science, obviously, given that mathematics plays such a crucial role in our scientific understanding of the world.
Right. It's like the language of science almost.
Exactly. But then you've also got these core metaphysical questions about the very existence and nature of mathematical entities. Are they real? What are they like if they are? And then on top of that, there are these deep epistemological puzzles about how we can possibly have knowledge of these seemingly abstract, non-physical things.
Yeah, it's like if numbers and sets and all that exist in some realm beyond space and time, how do our finite physical minds even grasp them? How do we know anything about them?
Precisely. And that's not even getting into the whole issue of how we do mathematics, the actual methodology, which, as you know, is very different from how we do science. It's much more deductive, starting from these basic principles, these axioms, and then building these elaborate structures of logical inference from them, quite different from the empirical observation and inductive reasoning we find in the natural sciences.
Right. It's all about proof and certainty in math, it seems. Like once a theorem is proven, it's not going to get overturned by some new observation or experiment like a scientific theory might.
Exactly. So there's this really interesting, almost unique flavor to mathematical knowledge, this apparent absolute certainty, this kind of permanence that's, well, it's pretty much unparalleled in other domains of knowledge. And that's another thing that makes it such a compelling target for philosophical analysis.
So with all of these fascinating puzzles in mind, our aim in this deep dive is to take you on a guided tour, so to speak, through some of the major philosophical perspectives that have been proposed to make sense of mathematics.
Exactly. We want to highlight those core questions that have captivated philosophical minds for centuries and to try and connect these, sometimes quite intricate abstract ideas in a way that really resonates with your philosophical sensibilities.
Right, to bring it all down to earth a bit without losing sight of the profound depth of these issues. So let's start with the basics, shall we? One of the most fundamental questions, as our source expertly points out, is ontological. What are mathematical entities? Like what are numbers, sets, functions, all of that?
Yeah, that's the million-dollar question, isn't it? And there are several major contenders on the table. Some say these mathematical objects are abstract entities that exist independently of our minds in the physical world. Others say they're concrete in some way, maybe even physical. And then there are those who say, nope, it's all in our heads. They're mental constructions. And even within these broad camps, there are tons of nuances and different ways of fleshing out these ideas.
Right, and tied up with the ontological question is the epistemological one. How is it even possible for us to know anything about mathematical entities, especially if there are these abstract things floating around in some realm beyond our senses?
Absolutely. That's a huge challenge for any view that takes mathematical objects to be abstract. Because, our standard accounts of knowledge, especially in a sort of broadly empiricist framework, rely on some kind of causal connection between the knower and the known. So, how do we, as embodied physical beings, make contact with this realm of pure abstract mathematics?
It's a good question. And then there's the issue of methodology. How do mathematicians actually do what they do? Like, what are the methods and practices that they use to arrive at their conclusions?
Right. And that brings us to the whole debate between deduction and induction. Mathematics seems to be largely, if not entirely, deductive. You start with these basic axioms, which are just taken as given, and then you use logic to derive theorems from them. And the chain of reasoning has to be absolutely airtight, no room for any kind of empirical evidence or guesswork.
Yeah, and that's a big difference from science, right? Where you're constantly testing hypotheses against the world, gathering data, making generalizations. In math, it's all about proof and absolute certainty.
Exactly. And this leads us to that final puzzle we touched on earlier, which is the status of mathematical knowledge itself. What kind of knowledge is mathematical knowledge? How is it different from, say, scientific knowledge or historical knowledge?
Right. It seems so much more certain, so much less revisable. Like we're pretty sure that 2 plus 2 will always equal 4, no matter what new discoveries we make about the universe.
Yeah, and that's another thing that makes it so philosophically intriguing. So those are some of the big overarching questions that we're going to be wrestling with as we explore the different philosophical perspectives on mathematics.
So where do we start?
Well, one natural starting point is a view called logicism, which, in a nutshell, is the attempt to reduce mathematics to logic. It's the idea that all mathematical truths are ultimately just logical truths dressed up in different clothing.
Okay, that sounds ambitious. I mean, to show that all the mathematics can be derived from just pure logic.
It is, and it's an idea that has some historical roots, actually. Leibniz, back in the 17th century, had some inklings of this. But it wasn't until the 19th century that a really systematic attempt to carry out this reduction was made.
And what spurred that?
A couple of things. First, there was the development of more rigorous mathematical theories in areas like arithmetic and analysis by people like Dedekind and Peano. And then there was Frege, who came along and developed a really powerful and expressive formalization of logic, second-order logic, it's called, which allows you to quantify over properties, not just individuals. This gave logicians a much more powerful tool to work with, and they thought, hey, maybe we can actually derive all of mathematics from this.
So Frege was kind of like the trailblazer of this logicist project.
He was. He spent years and years developing this incredibly detailed and sophisticated system, and he thought he'd succeeded in deriving the basic laws of arithmetic from just pure logic. It was a huge achievement.
But there's a but coming, isn't there?
Oh yeah, a big one. Russell, another brilliant logician and philosopher, discovered a fatal flaw in Frege's system. It turned out that one of Frege's basic principles, his basic law of V, as he called it, led to a contradiction, a paradox.
Oh, paradox. Those are always trouble.
They are. And this one was a doozy. It's called Russell's paradox, and it basically arises when you try to consider the set of all sets that are not members of themselves. According to Frege's basic law of V, this set should exist, but then you run into a problem. If it exists, is it a member of itself or not? If it is, then it shouldn't be, because it's supposed to be the set of all sets that are not members of themselves. But if it isn't a member of itself, then it should be, because it fits the definition. It's a classic contradiction.
Ouch, that sounds like a head spinner. So Frege's grand project hit a major roadblock.
It did. But Russell wasn't willing to give up on the logicist dream just yet. He thought there was a way to fix the problem, and he came up with his own system called the theory of types.
Okay, so what's that all about?
Well, the basic idea is to prevent these kinds of self-referential paradoxes by introducing a hierarchy of types. So you start with individuals at the bottom level, then you have properties of individuals, properties of properties, and so on. And the rule is that you can only apply a property to something of a lower type.
So you can't talk about a set being a member of itself, because sets and their members are on different levels of this hierarchy.
Exactly. That's the basic idea. It's a way of imposing a kind of logical order to avoid these vicious circles.
Clever. Did it work?
Well, it did prevent the paradoxes, but it came at a cost. Russell found that even in this type theory, to derive the basic laws of arithmetic, he needed to add in some extra axioms that didn't seem to be purely logical truths.
Oh, like what?
Well, the most famous one is the axiom of infinity, which basically says that there exists an infinite collection of things. And that's a pretty big assumption. It's not something you can just derive from pure logic. It's more like a metaphysical postulate.
Right. So even with all this fancy type theory, you still need to make some pretty hefty ontological commitments to get mathematics off the ground.
You do. And that led some people to think that maybe the whole logicist project was doomed to fail. But, philosophy never really gives up that easily. And in the 1980s, there was a kind of revival of logicism called neologicism.
Neologicism?
Yeah.
So what's new about that?
Well, a philosopher named Crispin Wright took another look at Frege's work and noticed something interesting. He realized that Frege's derivation of the laws of arithmetic could be broken down into two steps. The first step used basic law of V to derive something called Hume's principle.
Hume's principle. And what's that?
It's a principle about numbers, and it basically says that two concepts have the same number of things falling under them if and only if there's a one-to-one correspondence between those things. Like, there are the same number of fingers on my left hand as on my right hand because you can pair them up one-to-one.
Okay, that makes sense. So how does this relate to Frege's system?
Well, Wright noticed that once Frege had derived Hume's principle, he didn't need basic law V anymore to derive the rest of arithmetic. He could just use Hume's principle and standard second-order logic.
Interesting. So the idea is that maybe Hume's principle itself is a logical truth, even if basic law V isn't.
Exactly, and Wright argued pretty persuasively that it is. Others, like George Boulos, showed that Hume's principle is at least consistent, which is a good sign. So this led to this whole neologicist program of trying to ground arithmetic in Hume's principle instead of basic law V.
So it's like a second shot at logicism, but starting from a different foundation.
Exactly. And it's still a live debate whether Hume's principle really is a logical truth or not. But it's an interesting approach because it suggests that maybe we can get away with weaker ontological commitments than Russell's theory of types required.
Right, because Hume's principle is just about equinumerosity. It's not saying anything about the actual nature of numbers themselves.
Right. And this whole focus on Hume's principle has led to a broader interest in what are called abstraction principles in philosophy of mathematics. These are principles that, like Hume's principle, introduce new objects into our ontology based on some equivalence relation between pre-existing objects or concepts. And philosophers are now trying to develop general theories of what makes an abstraction principle acceptable or not.
Okay, so logicism, even in its revised form, is still a contender in the philosophical arena. What's next on our list?
Well, let's shift gears a bit and consider a very different approach. Intuitionism.
Intuitionism. That sounds, well, intuitive.
It does, but it's actually a pretty radical view. The basic idea is that mathematics is not about discovering some pre-existing realm of mathematical objects, but about constructing them in our minds.
So it's all in our heads.
Well, not exactly. Intuitionists don't deny that there's an external world, but they say that mathematical objects are not part of it. They're mental constructions created by an idealized mathematician through a series of mental operations.
An idealized mathematician.
Yeah, it's kind of like an abstract model of a perfect mathematician, someone who can carry out any mathematical construction you can imagine without any limitations of time or memory or anything like that.
Okay, so it's not just about what I can construct in my head. It's about what's possible in principle for this perfect mathematical mind.
Exactly, and even this idealized mathematician is still subject to certain constraints. For example, they can't actually complete an infinite construction because that would take an infinite amount of time. It can only ever perform a finite number of steps in any given construction.
So intuitionists reject the idea of an actual completed infinity.
They do. They only accept the potential infinite, the idea that we can always keep going, always add another element to a sequence, always perform another step in a construction. But we can never actually reach the end, never grasp the completed infinite.
Interesting. And this has some pretty significant implications for logic, right?
Oh, yeah, big time. Because intuitionists reject the actual infinite, they also have to reject some of the basic principles of classical logic, the kind of logic that most mathematicians use without even thinking about it.
Like what?
Well, the most famous one is the law of excluded middle, which basically says that for any proposition, either it's true or its negation is true, there's no middle ground.
Right, that seems pretty basic.
It does. But intuitionists say it doesn't hold for propositions about infinite collections. Because if you can never complete an infinite construction, you can never definitively say whether something is true or false for all the elements of that collection.
Okay, I see. So they have to develop a different kind of logic.
They do. It's called intuitionistic logic, and it's much more careful about how it handles statements about the infinite. And this leads to a different kind of mathematics, too. For example, there's something called Heyting arithmetic, which is the intuitionistic version of piano arithmetic.
And is that very different from regular arithmetic?
It is, especially when you get into more complex areas of mathematics like analysis. Intuitionistic analysis is a very different beast from classical analysis.
So intuitionism is a pretty radical departure from the way most mathematicians think about things.
It is, and that's one of the reasons why it hasn't been as widely embraced by the mathematical community as other views. But it's still a very important and influential perspective because it raises some really deep questions about the nature of infinity and the limits of our mathematical knowledge.
Okay, so we've got logicism, which tries to reduce math to logic, and intuitionism, which emphasizes the constructive, mental nature of math. What's next?
Let's talk about formalism. This is a view that was very popular in the early 20th century, largely thanks to the work of David Hilbert, one of the greatest mathematicians of all time.
Hilbert, that name rings a bell.
He was a giant in the field, and his approach to mathematics was very influential. He was kind of sympathetic to the intuitionists in that he thought that the natural numbers were somehow more fundamental than other mathematical objects, but he didn't think they were mental constructions. He thought they were more like concrete symbols, things you could actually write down or represent physically.
Okay, so he was a bit more grounded than the intuitionist.
Well, he was. But when it came to higher mathematics, like calculus or set theory, he took a more instrumentalist view. He thought of these theories as basically formal games played with symbols according to strict rules.
So not about actual objects or mental constructions, but about manipulating symbols.
Right. And the point of this game, for Hilbert, was ultimately to prove things about elementary arithmetic, which he did think was meaningful, and about real things, these quasi-concrete natural numbers.
So it's like higher mathematics is a tool for proving things about the more fundamental parts of math.
Exactly. And Hilbert believed that any arithmetical truth that could be proven using higher mathematics could, in principle, also be proven directly within piano arithmetic, even if the proof would be much more complex and difficult.
So he was very confident in the power of arithmetic.
He was. He even suspected that every well-formed question in arithmetic could be definitively answered, either proven or disproven within piano arithmetic. But he also recognized that sometimes it's much easier and more insightful to take a detour through higher mathematics to get to those answers.
Right, it's like taking a shortcut through a more abstract landscape to get to your destination.
Exactly. And Hilbert was also very concerned with the consistency of these formal systems. He realized that if a system is inconsistent, if you can derive a contradiction within it, then you can prove anything, which basically makes the system useless.
Right, because if you can prove both a statement and its negation, then logic breaks down, and you can't trust in any of the conclusions you derive.
Exactly. So Hilbert and his collaborators embarked on this ambitious project, known as Hilbert's program, to try and prove the consistency of higher mathematics using only the methods of elementary arithmetic, which they considered to be more secure and intuitively grounded.
So it was all about finding a solid foundation for mathematics.
It was. But then came Gödel and his famous incompleteness theorems.
Ah, Gödel, another big name in the history of mathematics. And his theorems kind of threw a wrench in Hilbert's program, didn't they?
They did, big time. Gödel's first incompleteness theorem showed that in any sufficiently powerful and consistent formal system, there will always be true arithmetical statements that cannot be proven within that system.
So even if your system is perfectly consistent, there will still be things you can't prove.
Right. And his second incompleteness theorem was even more devastating. It showed that no consistent formal system can prove its own consistency.
So you can't even prove that your system is free from contradictions using the system itself.
Exactly. And that was a huge blow to Hilbert's program because it meant that you couldn't use arithmetic to prove the consistency of higher mathematics as Hilbert had hoped.
Wow, so they kind of put a limit on what formal systems could do.
It did, but it didn't completely destroy the formalist approach. Some philosophers, like Haskell Curry, took a more pluralistic view. They said, okay, maybe there's no single, all-encompassing formal system that can capture all of mathematics, but we can still think of mathematics as a collection of different formal systems, each with its own strengths and weaknesses.
So it's like a toolbox of different systems, and you choose the right tool for the job.
Exactly. And the choice of which system to use might be based on pragmatic considerations, like its consistency, its simplicity, or its usefulness for certain applications.
That makes sense, but doesn't that kind of miss the point of mathematics? Like most mathematicians think they're discovering real truths, not just playing games with symbols.
That's a common objection, and it's true that many mathematicians don't feel like they're just choosing arbitrary systems. They feel like there's a sense in which some systems are more correct, more true to the nature of mathematical reality than others.
Right, like there's a right way and wrong way to do math, even if you can't always prove it.
Exactly. And that's something that formalism, at least in its most radical forms, struggles to account for. But there have been attempts to salvage parts of Hilbert's program. For example, Michael Detlefsen has argued that we might still be able to prove the consistency of those parts of higher mathematics that are actually used in proving things about arithmetic, even if we can't prove the consistency of the whole system.
So maybe there's a kind of core of mathematics that is more securely grounded than the rest.
Maybe. And there are also those who think that Gödel's theorems don't really show that arithmetic is incomplete, but rather that our current formalizations of arithmetic are just not expressive enough. Daniel Isaacson, for example, has argued that piano arithmetic might be complete in a certain sense, but that the unprovable truths that Gödel identified only become accessible when we move to a more powerful language, a higher order logic.
Interesting. So maybe the limitations are not in arithmetic itself, but in our way of talking about it.
Exactly. So formalism, like all the views we've discussed so far, is complex and nuanced, and there's a lot of debate about what it really means and what its implications are.
Okay, so let's move on to the next view on our list. Predicativism. What's the story with that one?
Predicativism is a bit less well known than some of the other views we've talked about, but it's still an important perspective. It arose out of the work of Bertrand Russell and Henri Poincaré, who were both deeply concerned with the paradoxes that had been discovered in set theory.
right? The paradoxes, like Russell's own paradox.
Yeah.
Those are a big problem for early set theory.
They were. And Russell and Poincaré thought that the root of these paradoxes lay in what they called impredicative definitions.
Impredicative definitions. And what are those?
Basically, they're definitions that define something in terms of a totality that includes the thing being defined. It's like a circular definition.
Okay, I think I see. Can you give an example?
Sure. Imagine you're trying to define the smallest number in a set. You might say it's the number that's smaller than all the other numbers in the set. But that definition is impredicative because it defines the smallest number in terms of the set of all the numbers, which includes the smallest number itself.
So it's like defining something in terms of itself, which is always going to lead to trouble.
Exactly. And Russell and Poincaré thought that these kinds of definitions were inherently problematic, that they violated a kind of vicious circle principle of logic.
So predicativism is all about avoiding these impredicative definitions.
It is. It's the idea that you should only define things in terms of totalities that are already well-defined, totalities that don't depend on the thing you're trying to define.
Okay, that sounds reasonable. But how do you actually do that in practice?
Well, Russell developed his theory of types, which we talked about earlier, as a way of preventing impredicative definitions. But as we saw, that system was pretty complex and unwieldy.
Right, it had all those different levels of types and all those restrictions on what you could say about them.
Exactly. So another mathematician and philosopher, Hermann Weyl, took up the predicativist cause and tried to develop a more workable version of it. He started with the natural numbers, which he took as given, and then he tried to build up the rest of mathematics in a way that avoided impredicative definitions.
And how did that go?
Well, it turned out that a surprising amount of mathematics could be done predicatively. Weyl was able to reconstruct a lot of classical analysis without using impredicative definitions.
Wow. So maybe predicativism is not as restrictive as it seems.
Maybe not, but it does run into problems when you get into more advanced areas of mathematics, like set theory, because a lot of the basic principles of set theory, like the power set axiom, are inherently impredicative.
So it's kind of a trade-off. You gain greater security by avoiding impredicative definitions, but you also limit what you can do mathematically.
Exactly. And that's why predicativism hasn't been as popular as some of the other views. But it's still a valuable perspective because it forces us to think carefully about the foundations of our definitions and the potential for circularity in our reasoning.
Okay, so that's predicativism in a nutshell. What about Platonism? That's the view that most people probably associate with mathematics, right? The idea that mathematical objects exist out there in some abstract realm.
Yeah, Platonism is probably the most intuitive view for most people, especially for working mathematicians. It's the idea that numbers, sets, functions, all of that are real things, just as real as tables and chairs, except that they exist in a different realm, a realm of pure abstract entities.
So it's like there's this whole other world out there, a world of mathematics, that's just as real as the physical world we live in.
That's the basic idea. And it's a view that's been around for a long time, going all the way back to Plato himself, who believed that the world of forms, which included mathematical objects, was more real than the world of appearances we perceive with our senses.
Okay, so it's got a long and distinguished pedigree.
Yeah.
But how do Platonists explain how we can know anything about these abstract mathematical objects?
Well, there are different versions of Platonism, and they have different answers to that question. One of the most famous Platonists was Kurt Gödel, who we talked about earlier. He was a very strong Platonist, and he believed that we have a kind of special faculty of intuition that allows us to grasp mathematical truths directly.
Intuition, like we just kind of see these mathematical truths in our minds.
That's the idea. Gödel thought that this mathematical intuition was analogous to our perception of the physical world. Just as we see tables and chairs, we can also see mathematical objects and the relations between them, even though they're not physical objects.
Okay, but that seems kind of mysterious. Like, how does this intuition work? And how do we know it's reliable?
Those are good questions, and they're questions that Gödel himself wrestled with. He thought that mathematical intuition was fallible, that we can make mistakes, but that it could be trained and refined, just like our perception of the physical world can be trained and refined.
It's like a skill that you develop over time.
Exactly. And Gödel thought that this intuition gave us a kind of intrinsic evidence for mathematical truths. He thought that some mathematical axioms, like the axioms of Zermelo-Fraenkel set theory, were just self-evidently true, that we could see their truth directly through intuition.
But he wasn't always so confident about his intuition, right? Like, he thought that there might be some mathematical questions that were just beyond the reach of our intuition.
He did. He He was particularly concerned about the continuum hypothesis, which is a very famous unsolved problem in set theory. He thought that it might be independent of the standard axioms of set theory, meaning that you couldn't prove or disprove it from those axioms. And he thought that maybe our intuition just wasn't strong enough to tell us whether it was true or false.
So even for a staunch Platonist like Gödel, there were limits to what we could know about the mathematical realm.
There were. But he also thought that we could gain evidence for mathematical truths in other ways, through what he called extrinsic evidence. This is evidence that comes from the consequences of accepting a certain mathematical principle, like its fruitfulness in proving other theorems, its explanatory power, or its simplicity.
So it's like you test a mathematical principle by seeing how well it works in practice.
Exactly. And Gödel thought that this kind of extrinsic evidence could provide strong support for a principle, even if we didn't have direct intuitive access to its truth.
Okay, so that's one version of Platonism. What about other versions?
Well, another influential approach is what's called naturalized Platonism, which is associated with philosophers like W.V.O. Quine and Hilary Putnam.
Okay, naturalized Platonism. What's natural about it?
Well, it's natural in the sense that it tries to ground our belief in mathematical objects in our best scientific theories. Quine was a very influential philosopher of science, and he argued that we should only believe in those entities that are indispensable to our best scientific theories. And Putnam applied this idea to mathematics. He said, look, mathematical entities are all over our best scientific theories. We use them to describe everything from the motion of planets to the behavior of subatomic particles. So if we're going to be realists about science, we should also be realists about mathematics.
So it's like the success of science gives us reason to believe in the reality of mathematical objects.
Exactly, and this is often called the indispensability argument for mathematical Platonism. The idea is that mathematical objects are indispensable to our best scientific theories, and therefore we should believe in their existence just as we believe in the existence of electrons and quarks.
That's a pretty compelling argument. But are there any problems with it?
There are. One common objection is that it's not clear that mathematical objects are really indispensable to science. Maybe we could reformulate our scientific theories in a way that doesn't refer to them. Or maybe the role they play in science is just metaphorical, not literal.
Right, like maybe they're just useful tools for modeling the world, but they don't actually correspond to real entities.
Exactly. And there are also concerns about the scope of the indispensability argument. Like, if it only supports the existence of those mathematical objects that are actually used in science, what about all the other mathematical objects that mathematicians have discovered?
Good point. So it's not a knockdown argument for Platonism.
It's not, but it's still an important and influential argument, and it's one that continues to be debated by philosophers of mathematics.
Okay, so we've got a couple of different versions of Platonism on the table. What about alternatives to Platonism?
Well, one alternative is what's called structuralism, which we touched on briefly earlier. The basic idea of structuralism is that mathematics is not about individual objects, but about structures.
Structures. Like what kind of structures?
Well, think about the natural numbers. They have a certain structure.
Yeah.
There's a first number, 0, then a next number, 1, and so on. And there are operations you can perform on these numbers, like addition and multiplication, and these operations obey certain rules. So the structure of the natural numbers is this whole system of relations and operations.
Okay, so it's not about the individual numbers themselves, but about how they're related to each other.
Exactly. And structuralists say that this is true of all mathematical objects. They're not individual things, but places in a structure.
Places in a structure. That's an interesting way to put it. So what about the structures themselves? Do they exist?
That's a good question. And there are different versions of structuralism. Some structuralists, like Stuart Shapiro, are Platonists about structures. They think that structures exist in some abstract realm independently of any particular instantiation.
So they're like the forms in Plato's philosophy.
Yeah, kind of. But other structuralists, like Jeffrey Hellman, are nominalists about structures. They think that structures don't exist as separate entities, but only as patterns or relations between concrete objects.
So there's no separate realm of mathematical structures, or just ways of organizing the things in the world.
Exactly. And this kind of nominalist structuralism is often called structuralism without structures.
Okay, so there are a couple of different ways to be a structuralist. What are the advantages of this view?
Well, one advantage is that it seems to avoid some of the problems of Platonism. For example, it doesn't have to explain how we can know about abstract objects because it doesn't think there are any.
Right, if structures are just patterns in the world, then we can know about them through our ordinary senses.
Exactly. And it also seems to avoid Benes-Haras' identification problem, which we talked about earlier.
Remind me, what was that problem again?
It was the problem of how to identify mathematical objects with sets. Like, if numbers are sets, which sets are they? There are lots of different ways to define numbers as sets, and they all seem equally good.
Right. And that made it hard to say what numbers really were.
Exactly. But structuralism sidesteps this problem by saying that numbers aren't sets, they're places in a structure, and it doesn't matter which particular set you use to represent a number as long as it occupies the right place in the structure.
So it's like the structure is the thing that matters, not the particular objects that make it up.
Exactly. And that's one of the main appeals of structuralism.
Okay, so structuralism is a pretty neat solution to some of the problems we've been discussing. What about other alternatives to Platonism?
Well, another one is fictionalism. This is a view that was developed by Hartree Field, and it's pretty radical.
Fictionalism. So it's like saying that mathematics is just a story we tell ourselves.
Kind of. Fictionalists say that mathematical statements are like statements in a work of fiction. They're not literally true, but they're true within the context of the story.
Okay, but that seems kind of weird.
Yeah.
I mean, math is so useful. It describes the world so well. How can it be just a fiction?
Well, fictionalists say that the usefulness of mathematics is kind of a mystery. They don't really have a good explanation for it. But they say that just because something is useful doesn't mean it's true.